So now I hope you should see.
Yeah, you can see your slides.
Okay. Thanks for the introduction and thanks also for inviting me to give this plenary talk. This is a topic which is maybe not my base research area because I am developing rehabilitation robots, including therapy machines, including also assistive devices such as special powered prostheses as well as exoskeletons and exosuits. But in my daily work and in my work also as a speaker, I realized a certain curiosity or expectation of the people, especially the non-experts, expecting that there are already prostheses around and robots around which are outperforming us humans. Robots such as Terminator or Iron Man. And I always have to say, no, we are not that far yet. And this inspired me to do a comparative study where we compared humans with robots. That's how I came to this topic and also to this talk. So, do robots outperform humans in human-centered domains? If we want to compare, just a moment. If we want to compare the performance of humans and robots, it's of course a question. Oops, now something blocked. Okay. If you compare them with respect to what? So we can compare mechanical performance, we can perform optical performance. And here I would say robots do outperform humans just from the point of view that they're not aging or not aging so much. As you see here, the robot from Ishiguro and our colleague Ishiguro is kind of struggling with the fact that he's aging faster than his own robot. We for sure can say that robots do outperform humans in remote environments, such as on Moon or Mars or in the deep sea, because here are areas where we maybe do not want to go or we are not able to go because of the missing atmosphere or the high pressures. But the question is especially interesting when we compare human environments. If we have robots that can outperform us so much that they can really help us or replace us in our own environments. So, some of our robots which are successful, like the Roomba robot for vacuum cleaning or robots for cutting the meadow in the garden. But they might outperform us for the task of vacuum cleaning because they're able to go beneath the bed and they're reaching areas which we cannot reach. But they're only outperforming us for vacuum cleaning tasks. They cannot cook for us, neither they can transport something into my car and so on. So they have a missing versatility. So they cannot do too much. Of course, there's a spelling error, versatility. So the robots we want to have in our human-centered environments need to have certain properties. They must negotiate on rough terrain, maybe in the garden, or be able to walk steps. That's why probably it's better to have legs rather than rows. Furthermore, they should fit through narrow spaces, for example, through doors or through crowds of humans. So they should have a slender appearance, not flat on the ground, but tall on the standing. They should be able to reach to tables or shelves just to oversee them with cameras, but also to interact them, to grasp objects, for example. They must also be able to perform energy. So passive walking machines are not satisfactory. They need to be able to carry objects from A to B. And that's also why we exclude flying machines, because their payloads are maybe too little for many of the tasks we need to do in our daily life environments. They also must have fingers and arms to be able to perform manipulations. At least the robots we were investigating should have a possibility to be added by arms and fingers so that they could do additional tasks. And they must be able to perceive the environment, of course, not only to control their own movement, but also to understand the problem, to understand the context. And that's why, of course, we need different kind of sensors. And since they should also work in indoor environments, they should be not too loud and not produce exhaust gases as we get them from combustion machines. That's why we end up automatically with humanoid robots. If you want to compare humans with robots, we don't need to compare only humanoid robots. But if you speak about humans and robots in human-centered domains, then we end up with humanoid robots, which have similar shapes, anatomy like we have. Now, the next question is, what do we want to compare in detail? We can compare functions, which humans do. Are they able to be done also by robots? But we can also compare structures. Are the motors better? Are the joints better? Are the sensors better in the robots compared to the human? What we did in our study is we did compare both. But then the question is, there are some functions in our humans, in us, which do not make sense maybe to be compared. For example, the fact that we are aging, that's more disadvantage. So we exclude that function, for example. The feeling of emotion, that's maybe something too complicated. We also excluded that in our study. And also the fact that our humans can reproduce, we can reproduce, is something which we exclude. We don't want to develop a sex machine. So we want to develop robots which help in human-centered domains for mechanical tasks. And also the aspect of digestion is, of course, very important for us humans, that we can eat, and that gives us power. But in the robots, the power, the charging works in a different way. The robots don't need to eat or drink. We just need to charge them. That's why we also exclude such aspects. On the robot side, we also exclude the aspect how they are being produced, and how they are aging from a technical point of view. So what is remaining are functions which are supportive for our daily life activities, which includes walking, learning of movements, calculating to process sensory information, for example, perception. But besides walking, we have many other mechanical tasks, such as grasping, such as manipulating objects. And all of this consumes energy. That's why it's also important to be compared between robots and humans. With the structures, it's a similar problem. We exclude the digestive system, the reproductive system in humans, and we also exclude propellers and wheels on the robot side with the argumentation as I had before, that we want to have machines which are able to interact with humans in human-centered domains. The leftovers are then structures such as eyes or cameras, hands, legs, the brain or computer, and then the energy source. Now, the study we did is already some years ago, so we have included all robots which were known to that time, or most of them. Some of the famous robots which have nowadays, like the Optimus from Tesla, we did not include in that intensity as we included these machines, as you see here. This is just a sub-choice. We have found more than 30 human robots, which made sense to compare. So the newest ones, but also some older ones. Here you see some of them. We also included four-leg machines. You see some of them here. And then we compared functions. For example, walking and running. You see for running, I mean, to compare walking, it's easy to outperform the humans with the robots. Many of them can walk faster than we can. With running, it gets more exciting. Here you see some of the robots which are well known, like the Atlas, for example, or the Asimo from Honda, Big Dog from Boston Dynamics. And they walk with speeds, the maximum speeds we could find in the literature or technical data sheets was up to about 2 or 3, maybe 4 meters per second. That's about 12 to 14 kilometers per hour. That's a good performance for these machines. I mean, it's amazing how well they can walk nowadays. If you take a human jogging, it's always faster. And however, there's one robot which is outperforming also the other robots. That's the MIT Cheetah. That can run up to about 6, 7 meters per second. So that's more than 20 kilometers per hour. It's faster than a human jogger, but if a human is sprinting and you don't need to take Olympic star, just a normal human, less athletic, sprinting is faster than the fastest robots we have nowadays, legged robots. Now, this is just the absolute numbers of walking speed which we found, or running speed which we found. It could be an unfair comparison if we don't normalize by some important denominators. So imagine if you take a very, very big robot, as large as a house, and if you're able to power it, gets very heavy and large, but probably such a robot has an easy job to outperform us, because if they just do single steps, slow steps, and one step is like 10 meters of width, then they can outperform us probably easily, but on the cost of size and weight. And that's why we have taken some denominators to normalize these functions of walking, running, and also for other functions. And the denominators were energy consumption, operation time, size or volume, and mass. And if you now normalize by mass, for example, and you see here on the x-axis it's the mass, and on the y-axis it's the running speed. That's just a sub-collection of those devices where we had reliable data of running speed and mass. Then you see that the most robots are beneath that line, the dashed line, which is a line for change my pointer for the human, but that's a jogging human. You see a human with a weight of, for example, 70 kilograms, jogging about 3 meters per second, which is more than 10 kilometers per hour. But there's again the cheetah. It's quite lightweight, only about 35 kilograms, which gives it an advantage because with a small size, it can run rather fast. So the speed in relation to the mass is amazingly high. So that's where this point is far above that line of the jogging reference human. But if you take there are the other devices. The Atlas, for example, is quite heavy. That brings it further down. It's running fast. It's running with about 2.5 meters per second, but its high weight is giving it a disadvantage. Same with Big Dog. But the MIT Cheetah has here great, it's outperforming the jogging human. However, if you take again the human athlete, then we can say, okay, it's about in the same range when we take the speed and normalize it by the mass. So, but if you take operational time of machines, unfortunately, most of the machines, they don't work so long because the batteries get empty. You see, for those devices where we got data, they can work up to about 1.5 hours. Atlas, for example. Cassie is a bit better. It's about 3 hours of operational time. But I would say, if you take our charging is eating and drinking, I think we can easily walk, take a hike without eating and drinking for about 5 hours, probably longer. So we do outperform the robots, not vice versa, with respect to operational time. Stair climbing. Here now you see some robots which can do stair climbing, where we got data normalized by the mass of the robot. And there's some which are outperforming the human for normal stair climbing. And that's the human, again, we take here the 70 kilograms, and we take a normal stepping speed of about 1.4 steps per second. That's a comfortable walking speed. If you run up the stairs, you see here some of the well-known devices. Honda is on the speed. It's walking stairs like humans in a comfortable speed. Cassie, again, is here outperforming the slow walking human. But if you walk upstairs faster, then we do outperform all of the known robots. Known means we published a study 2 years ago, and the data was about 3 years old, 3 or 4 years old. Other functions. Now, there are robots which have been developed to do these tasks, like only jumping or swimming in water, then crawling on ground, grasping objects, manipulating objects, driving a car, making a backflip. And in most of these tasks, the robots do not outperform the human. Of course, there are some amazing tasks. Make a backflip, the Atlas robot, the old one, hydraulic one. Or lifting objects, maybe. There's some robots which are very strong. I would say at least as good as athletic persons. But I would not say that the best robots do outperform the best humans, which are maybe athletes. Furthermore, the robots we found who can do, for example, backflips, they don't show the same versatility like humans do. So they can maybe do backflips and they can also jump, maybe even drive a car, but they cannot swim. Or Atlas, the one which can make backflips, cannot grasp objects because it doesn't have hands with fingers. And if they would be added to the device, maybe then the robot could not do anymore the backflips. So the versatility is really in the human much better. You know, probably these movies from the old Atlas robot, that movie is maybe 4 years old. It's amazing what the robot can do, but again, the versatility of humans is not there. And humans, the best humans can also do this. And what we know from Mark Rybert, who admits this himself, is that it takes some trials to get these movies. The movies are, of course, not fake, but it might need some maybe 10 repetitions to make it, to get it like this. And you have a team of engineers behind tuning the robots. Now let's see with the structures. Yeah? To summarize the function, I would say there are some robots which are as good as the humans, as average humans, but just in single tasks. What's about the structures? Motors, for example. If you take characteristics such as power density, here we also normalize by mass, for example. That's why we speak about power density, also force density, energy efficiency. Then we can say that there are motors which are outperforming the human already. There's a little but. The but is that some of these actuators, for example, the fluidic ones, pneumatic one and the hydraulic ones, they are tethered. They are cabled with tubes, hoses, for the supply of the pressurized air or pressurized oil. And often the energy or the pressurized liquid is outside of the robot. That's why they are tethered. And also the compressor in the hydraulic ones is often outside, far away from the robot. And then you can make the mass of the device quite reasonable. You know, with Atlas, we have everything on board and it still has a quite good power to weight ratio. So in a more detail, you see here some numbers of the human muscle, power density, power efficiency, force density. If you take electromotors, hydraulic cylinders, pneumatic cylinders, electroactive polymers, and shape memory actuators, we see that most of the parameters or characteristics are better in the machines, all of them actually, or not almost all of them. In pneumatics, you see the efficiency of pneumatic cylinders is not so good because they have a lot of friction. So the muscle is also not so good, 20 to 40%. But electromotors or hydraulic cylinders do outperform the human muscle with respect to power efficiency. So you see, with motors, actuators, at least when they're tethered, they're easily outperforming human muscle with respect to these characteristics, of course, not with respect to self-healing or such stuff, which we did exclude at the beginning. What's about the materials and the strength, braking strength, elastic properties, weight in relation to the weight? Here, when the bone is amazingly strong, but in the meantime, we have materials like carbon, which have a better strength to weight ratio. What's about joint friction? Human joints are very nicely lubricated with some liquids. Friction is rather low, thanks also to special pairing of different materials, the cartilage in the joints, for example, including the lubrication. But ball bearings are better than human joints. Other bearings, friction bearings, are usually worse than the human joint, but the ball bearings easily outperform human joints. What's about motion sensors, such as to measure joints, joint angles, sensors to measure speed and accelerations, such as done by IMUs, and force sensors to measure forces, torques, but also pressure. Here we have a large choice of many different sensors, which are commercially available, many of them, and they're easily outperforming the accuracy of our human sensors. Cameras, that's an exciting, although a bit complicated aspect because there are many characteristics which we can compare when we take a technical camera and compare it with a human eye. And you see, when we combine conventional CCD or RGB cameras with event-based cameras, if you take both of them, then I can tell you we can even outperform the great human eye. You see it more detail in this table. Some of the characteristics of the eye, including the size, power consumption, field of view, spatial resolution, temporal resolution, color range, luminance, depth perception. If you take now different kind of camera systems, CCD, CMOS, event-based, and 3D LiDAR, you see now green that they are either one technology or the other technology outperforming the eye. So if you would combine them, then we are quite good with the technical side. We are outperforming, or let's say at least as good as the human eye. What's about power, computational power? Of course, if we take terms like intelligence, human intelligence, our ability to solve problems, to adapt to new situations from our cognition, that's very difficult to outperform by a computer. But using a computer to control movement, complex movements, I would say with respect to computational time and memory storage, the computers are outperforming the human brain easily, at least if you take a big computer or a cloud of computers. So now in the last months, we saw great movies, and I'm watching social media. There were about a year ago, first movies from the Tesla Optimus robot, and now just recently, some days ago, we saw other great movies from the new Atlas from Boston Dynamics. And it's amazing how well they can perform, what kind of motor tasks they can do, including crawling, making different kind of jumps. But when you look carefully, for example, with the latest movies from Tesla, as an expert, I'm still not convinced. I think it's still just mania hype. So the robot, I saw some movies where Optimus is grasping eggs. But I didn't see any movie the robot is opening the egg and putting it into a saucepan. Robot can carry objects, but it looks a bit shaky, and the objects look a bit lightweight. They don't look heavy. I don't believe that they are carrying high weights. Furthermore, they can fill a glass of beer using a tap, but I did not see any robot yet taking an opener and opening a bottle, with this little Kronkorken. And they can serve our humans, but only as long as the battery holds. Maybe after 1 or 2 hours, they're useless, or they have to get recharged and they're not available to serve me. So that's why I'm still very skeptical. To summarize, robotic structures in general are better than human structures already. That's amazing. However, somehow we were not able as engineers to make a systematic approach to combine these structures in a way that we're also getting better functions. That's a bit surprising. And I believe it's just a matter of time to make the robots better. What we need is we have to include better motion intelligence. We have to do better controlling and learning of the robots. Reinforcement learning is, of course, something very potential. We have to optimize the size and the arrangement of the structures to put everything into a limited space. And that's why I'm not too pessimistic. It's a matter of time, and I think it doesn't take too long that the robots will outperform the humans because they're getting better and better. But it takes more time than many people, at least the lay persons, believe. I still think it takes 10, 20 years maybe. Okay, thank you.
Thanks a lot. Thanks a lot. That's a really exciting talk. Yeah, we have a couple of questions from the audience, and then also I have a question to start. So yesterday we talked about a lot of a lot of us like talk about the smart bodies for robots, especially like intelligence of hardware, like robotic hardware, intelligence robotic hardware. So in your opinion, what are the main bottlenecks in the robot hardware to develop robots that outperform humans?
Yes. I think the hardware itself is not bad already. I mean, if you just take the main components like motors, sensors, the mechanical links, joints, um, they are great to solve specific problems. And we are able, as engineers and computer scientists and so on, biologists, to place hardware in a way that they solve one task. But as soon as we have a collection of tasks to be solved, the arrangement of the hardware, but also the control using control software is getting much more complicated. It's magnitudes of higher complexity. And we somehow fail to solve it. Have you ever seen a robot which can do these tasks very easily? You know, their robots is one of the tasks, but we can do it easily, and we can
Yeah,
additionally do different tasks. And um, and the robots fail these more complex tasks.
yeah, absolutely. Yeah. Yeah, we have a couple of questions from the chat. So there's a lot of interesting discussion going on in the chat about the power sources for such robots. For example, one question is like, could the digestive system be compared to a power source? Can you think of
Yeah,
like, yeah,
it's a good question to ask. Why don't we make some of our structures of the machines more biological? Um, And I believe indeed making components biological has a higher potential to succeed. Um, and I'm seeing it also from the point of rehabilitation engineering, prosthetics, for example. People think we can easily plug in cables into the spine to connect the spine with a machine for people with spinal cord injury, with complete rupture of the spine. But that doesn't work because this interfacing of technology with biology is always a challenge. If you make things more biological, then it's much easier. I believe it's easier to recover the damaged spine biologically in order to heal the people. Yeah. It's also probably easier to get maybe it's easier in the long run to get the highest power or charging in a biological way or chemical way using principles of digestion. It's not solved yet. Or if you lost a limb, we have animals which can recover because they grow new limbs, like lizards, some kind of lizards. But in a human, it does not work or not yet work. Now the question is, who will be faster, the engineers or the biologists and medical people?
yeah, I think that's the integration of every field, I would say. And, yeah. Okay, so we have another question actually related to humanoid robots, which is an interesting question. So it seems like humanoid robots have seen a surge in attention and the funding, for example, recently. So what do you think is driving this trend? Like, why do you think that we have like huge trend in humanoids?
Yeah, yeah, there are different reasons. Again and again, military is funding such projects. There is interest from military. Then maybe there's some coincidence. There's some guys, crazy guys like Elon Musk, who are suddenly spending a lot of money into robotic industry, and other companies are following. Um, we have Hollywood producing nice robotic movies. I don't know who was first. There's a chicken egg problem. Was the first Hollywood? Now we make the robots, or were first the good robots? Now Hollywood is copying them. Um, and now it's AI. Yeah, I don't know why at the moment there's such a push with robotics at the moment. In the last 2 years, you have so many new companies popping
Yeah,
out, developing robots and trying to sell them. Humanoid robots.
yeah, 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 exactly. We have another question actually. In your opinion, do these robots you have looked at, like for example, Atlas, Cheetah, Tesla? exhibit bodily intelligence, whether they have like intelligence in their body. And then there's a follow-up question, as in outsourcing of cognitive intelligence to mechanical properties of the body. I think that's an interesting question.
Yeah, that's a very important question. I still have to understand it. So the
Yeah, the first question is like, do
comparison of
robots, they have a like body, like I think it's related to my first question, like whether they have intelligence in their body.
yes, I mean the intelligence we have in our body, where we don't need a centralized brain, that's very powerful, and we should try to better understand our biological um, distributed intelligence, mechanical intelligence, and I think we should copy what's possible to copy and learn from it. But there was also relation to cognitive intelligence. I didn't get this.
Yeah, the second part is like, as in outsourcing of cognitive intelligence to mechanical properties of the body. How you link these two systems, I would say. But
Yes. I don't know what to say, but what I can say is that I think it's failed. Most robots we see nowadays, and I'm sure other robots which are now popping out, are not exploiting this kind of body intelligence. They're just considering a quite simplified way of we need to move in a certain way, we need a certain kinematic result, or maybe also kinetic result in terms of force interaction between the robot and environment. And then they use a position controller or force controller. Maybe they learn with reinforcement learning, and then you get a movement. And that's not how the body works. Yeah, we have much more distributed system. Large fraction of our movement comes from the spinal locomotion, spinal centers, reflexive centers, based on afferents or sensor information, of course. But we don't have some kind of perfect trajectory in our mind, which we try to follow with a PID controller. So,
yeah,
and we think we have to improve the robots a lot towards this direction.
yeah, I think, yeah. I think we have another really interesting question. So Hong asks, like, considering that the human body has inherent physical and functional limitations, would it be more advantageous to design robots without constraining them to human-like forms or functions? I think, let's say, why
Yes.
do we have like robots like humans or functions? Or
Yeah. So the environments where we live are not artificial. They have been developed with our evolution, with our cognitive evolution. So all the tools we're using, yeah, the shape of a pen is the shape of the pen has a shape because we have fingers and a certain size. All the kitchen instruments, the table sizes, the chairs we have, they're adapted to our anatomy. And if we would change them for the advantage of robots, then it would exclude us from our own environments. So I think we cannot change the shape of our environments as long as we want to play a role there. I still want to sit, even
yeah,
more maybe if a robot is assisting me. I want to still sleep, and I still want to eat, maybe with my own hands. And that's why I want to have devices which are shaped in according to my body.
yeah, yeah. I think, yeah, it's the synergy between environment and like, yeah, the humans. I think, yeah, that's really interesting. Yeah, Fumi has a question. So robots and humans are good in different ways, and wondering what are the good ways to cooperate to better function altogether. Any comments from your experience in Cybertron? Like, you have organized
Yeah.
this stuff.
I did not mention the application, the examples where we can have this, where we are desiring such kind of robots interacting with us. And I think one big field is care of persons, elderly people with disabilities, with muscle weakness, who really need support. And nowadays they get support either in the hospital only by care persons, by nurses and so on, but then have to stay in the hospital. If they go home, they need care persons at home or family members. And that's often failing because they're not there or too expensive. They cannot afford. So I think there's a great potential to have these people. It's a huge market because we're getting older and the risk for these needs are increasing, or the chances are increasing. Other applications are maybe entertainment. If you want to play sports against a robotic group, could be fun. But also in work environments. Here we must be careful because now there's a lot of about shared environments where we have robots in logistics together with humans, or where we have special impedance controllers where the robots can be guided by the human and so on. And I think that this kind of sharing of workspaces is, in most cases, just over a limited phase of time, because sooner or later these things can be done completely by robots only. But maybe there are some exceptions where we need still the humans together with robots in assembling areas in any kind of industrial work.
Yeah. I think kind of a follow-up question, because you talk about a bit of different applications. So there's one question from the audience. If we try to explore extraterrestrial environments such as Moon or Mars, would the humanoid robots make sense to try to investigate? Which environment could be challenging or dangerous for future human settlers? So I think that's a bit of futuristic.
Can you repeat somehow?
It's asking Leon asking about if you try to explore extraterrestrial environments such as Moon or Mars, would humanoids robots make sense to try to investigate which environments could be challenging or dangerous for future human settlers?
Interesting thought.
Yeah, interesting.
Yes. First of all, of course, I think that we just to be on Mars and to do something on Mars, we don't need humanoid structures. But of course, this question refers to preparing humans living spaces on Mars, for example. That could be a nice idea to send first the robots there to check out things before we send humans there. But then the robots should be already quite good. I think nowadays we are missing the versatility of the robots. We could send out different robots, maybe one robot for walking, using toilets, another robot for cooking, another robot for doing sports. That could work soon.
Yeah, interesting. I think we have a couple of minutes. So please send you any questions to chat. But in the meantime, I have another question. Because we talk about the mechanical or the mechanical intelligence, and then also you mentioned about the cognitive side of these robots. So, in your opinion, to make robots outperform humans, what are the main what is the main bottleneck? Is it because of the hardware, or is it because of yeah?
Yes, I think it's
or a combination of both.
It's a combination of both. I think, it's a combination of both. We need to, we still would be great to make the power density, for example, and the sensing density of the devices a bit better, to make them smaller. And then we have more freedom to arrange the components to a more complex system, which performs well. But we also need to train the software, to improve the software. We can do learning, emotion learning, using reinforcement learning, for example. But here we have an important limitation. So often people think, maybe not so much the expert joining this chat, but when I give talks to the general public, they are a bit spoiled by news such as Google Minds, or was it OpenGI? OpenGI, I don't remember.
Yeah.
Who developed this software which learns to play AlphaGo. And first it learned from, did imitation from existing games. In a later version, just some years ago, it was learning from just the rules itself. It was self-learning, self-driving. That works very well. It was very fast because it's only limited to software. As soon as you have to combine software with hardware, with mechanical movement, meaning also that the robot is interacting with the environment, with physics, and or with humans, biology. So if you, of course, we can learn from interaction with the physical environment and from interaction with the humans, but this learning is limited in time. We can only or mainly parallelize it by copying the machines and letting them learn together in parallel. So if you produce 1,000 robots, you can be 1,000 times faster. But the learning should also include an evolution of the technology. So we should also take into account that the hardware of the 1,000 robots must be replaced after a while, after it gained to a saturation of learning. You can replace it. Then again, you produce 1,000 robots that can learn from interaction with a human, but it's time limited. We cannot accelerate it because physics, our laws in the world are limited in time. That's why the learning speed and also the reproduction and update speed of the hardware and software is limited in time. That's why, it still takes a while until we have the best robots together with the best software.
Yeah, I think fantastic answer. Robert, I think we are come to the end of this session. And then, thanks a lot for your fantastic talk. It was truly inspiring. And then also we had a really good Q&A session. But Robert, like we do have another session after this, after the coffee break, kind of panel discussion. And then we have a discussion with all the speakers. So if you have time, please feel free to stay with us. Then you can kind of join that session as well.
Which time is that, Terence?
Just give me 1 second. Think. So we have the short talks from 10:30 to 12. So probably around because we have 4 speakers. So around 11:15, we should be starting this panel discussion. So if you are here, feel free
12:15. You say 12:15, right?
Not sorry, 11:15. Sorry, my bad.
Okay. It's London time. Sure. Yes. Thank you.
Yeah. Thanks a lot.
Thank you.
Yeah, thank you. And then let's take a break and then we have a coffee break, 15 minutes, and then we'll start the next session, the short talk and panel discussion at 10:30. See you.
Thank you.
Thank you.